Now, recording has started. Happy Garbage Day. Happy Tuesday to everyone. A lovely Tuesday. Got to go running this morning. That's always nice when I can find time to do that. Get my energy out so I don't show up manic, as I want to do on teaching days. We got the alternative due today, by the way, if you haven't tried this. This is Raspberry Lemonade Diet Mountain Dew. Highly recommend. It's lovely. There's a couple flavors, but regular Mountain Dew has a lot more flavors, not as much with the diet. But can't handle the sugar and the caffeine at the same time. Can you imagine if I showed up with a real Mountain Dew, what that would be like? It would be too much. That's what I can tell you. All right, so what have we been talking about so far? This is week 3. What's this class about? Start with softballs. What's this class about?
Longitudinal multi-level models.
Yeah, correct. The title. Yes, longitudinal. How many occasions do you need for it to be considered longitudinal? 2. Is 2 a good idea? No. With 2, you cannot differentiate what are true individual differences in change relative to measurement error around a constant trajectory. They are the same thing, indifferentiable. So we're heading past 2 occasions into more occasions. The example that I have today goes out of chapter 3, the second part, and it has 6 occasions. And we will beat this data set to death later on in unit 6, fitting all different kinds of models of change to those 6 occasions. Let's see what else. Why am I teaching this from a multi-level modeling perspective? That's the other part of the course name. It's easier than SEM. It starts from regression. So that's what we did last time, is we had E at the end of the equation, right? Assuming that everyone's independent and all the occasions are independent. If we don't want to make that assumption, or we can't because it's not true, what do? How do we fix it so far? How do we change the model to accommodate the fact that occasions from the same person are correlated? Partition E, add a random effect, zoomers for the win. Roomers, do you want to add anything to that? What is the letter that goes with the random effect in my notation scheme? U. Yes, and why did I pick U? Because it's you. You get one. You get one. I'm Oprah today. Also because I can draw U reliably with a marker. That is why. Other Greek letters people use for this is, I call it squiggle 1. I'm not sure what its real name is. There's also squiggle 2. Those are the ones I cannot draw at all. So those do not show up in my notation. Question, does adding a random effect basically mean controlling for time and person? It means controlling for person, I would say specifically, because the idea of a U is that each person gets a different mean, therefore adjusting their prediction for that. So the expression that you may have heard before from a design perspective is everyone is their own control. Like you have your own starting point and then what happens from there, right? Single case design, your own control, big idea, right? We're just going to do multiple case design. Yeah, we call that a multi-level model. Cool. We're going to get some new options though, because just U all by itself assumes something that is likely not tenable. It assumes that people differ from each other only in one way, in their mean. To put that another way, it assumes parallel change. Everybody changes the same. So all you need to do is give each person their own mean and you're good to go. You've controlled for all the personness in their trajectory. But what if that's not true? Well, then we got to do something else. So the next, 3-4 weeks are basically like options for what something else could be in terms of a pattern of variances and covariances over time. Only having U0, our random intercept, is equivalent to saying that the variance stays the same no matter what occasion it is, and the covariance stays the same. So in data where that's not true, this model will not be a good fit. All right, more folks. There we go. So any questions on any of that or other things you want to review or talk about? We now have both TAs in the chat, by the way, available to talk to if you don't want to talk to me. And by the way, those of you who are roomers can also be Zoomers at the same time if you want to talk to folks on, quietly. Anything else right now? Are you pointing? Are you thinking?
Thinking. So when we're measuring multiple times for the same person,
Mm-hmm.
like, does it have to be like the same conditions? Or can
Ooh.
it be different things? Or is it better if it's like a reversal where it's like baseline treatment, baseline treatment?
So I'm going to answer the first part of that because that was a beautiful segue into one of the things that we're going to talk about today. Could not have planned that better, so thank you.
All right.
His question was, when we're measuring people multiple times, do they need to be like the same conditions? Is that what you said?
Mm-hmm.
There's a vocabulary word that goes with that idea, where everybody's on the same measurement schedule. Balanced, yes. So it is easier if it's that way. You have more choices, but that's not a requirement of these models. So if we had more than 2 occasions in this picture, like if you picture like more purple dots around here, where the purple dots are don't have to be the same place as where the corresponding orange dots would be, because the line goes through whatever dots you have. So unbalanced is okay in these designs. It just limits your choices to some extent as to what you can do then, and it also makes it trickier to judge how well a model fits.
Okay. So with that as well, something else another professor has said is like when you're measuring the same unit across time, it's not actually like the same unit, because like that exposure changes it. Like is that true? Did I miss something or what?
I think it is true. So the statement was that even if you're measuring the same person repeatedly over time, they're not really the same person because the measurement process may have changed them. I think that is true. I don't think it's something that's easily controlled for, because in a non-experimental, like just a pure observational study, like the more times you ask people to do something, they get better at it, or they know what to expect. Like if it's a survey about attitudes or something, they may change their answers because they know what the questions are going to be, or if the questions are in the context of a different instrument, for instance, that may affect things. That we know that stuff happens, but to be able to tease that apart, you need a design in which you could do so. So let me give you an example of a design in which you could do so that's observational. A measurement burst design is a particular kind of longitudinal design in which you measure people a bunch of times over a short time frame, but then you repeat that assessment at a longer time frame, So in the context of, is it these data? Yeah, actually, the data we're going to be beating to death are from a measurement burst design study. They're from the first burst only. So the context is worrying about reactivity due to practice or repeated exposure in a cognitive speeded task. So these are older adults. They're asked to do something as quickly as they can, and at the same time that they are getting older, so you would expect performance decline, they're also getting practiced, and so those can kind of cancel each other out. Well, if you measure somebody and the second time you measure them, they're both practiced and older, what do we call that? Starts with a C. Confound, yeah. So we don't want that. So a measurement burst design, in the study where these data came from, what they did is make them do the same task 6 times over a 2-week period. Now, I don't know about you, but we can't really age over 2 weeks. It may have felt that way at the beginning of the semester, but we're not doing like true age-related decline over a 2-week period unless something happens to your health, and then that makes you a different problem. And so then they measure how quickly people's response times change as a function of just repeated exposure to this task. And then they do it again 6 months later. And so then we can look at how age affects things like optimal performance after you've had practice, or the extent to which you start sucking again because you haven't done it in 6 months, like the gap between where you left off and where you are. In educational settings, there's like a summer gap that, I don't know, there's a word for it, right? Loss of learning, I don't know. My son forgot everything he learned in 3rd grade, and now he's relearning it at the start of 4th grade, whatever you want to call that. Learning loss. Hey, I got it right. I'm an educational psychologist today. So you have to have a design that separates the possibilities in order for that to observe why this kind of change happened versus that kind of change. That's the long answer, and that's very tricky to do.
That's very helpful.
Okay. So you'd have to think of ways to try and disentangle what is a response to your treatment versus some other process that's causing people to behave differently.
Mhm.
I don't know how to do that. It's not my jam. But I bet you do. Or you know people that do. Yeah, I kind of do. All right. Other thoughts? Questions? No? Zoomers, we're still good? Cat, hello. Like seeing the pets wandering around. It makes statistics nicer if you're petting a cat, doesn't it? It's like a soothing sort of. I've had people, crochet in my class before, something to kind of keep their hands busy while they're listening. I had students walk on treadmills during the pandemic, during class. I'm not lying.
Yeah.
That actually made me happy because then they're getting their steps in. That meant the slides were detailed enough that they didn't have to like scribble everything down. It's a good thing. Anywho, all right, should we talk some new stuff? Now, new-ish is probably appropriate. I'm guessing you've seen this before, but I'm trying to present it in a way that allows us to build, as opposed to this is the end of the story. So in intermediate statistics, or your first-year stats class, one of the things that is commonly taught is repeated measures ANOVA. I deliberately chose not to do that in my version because I didn't want to get into all of these things. Repeated measures ANOVA has two choices for the model for the variance, and there are infinitely more that one should consider. The other part of it, why I don't do it, is because to do it properly, to avoid listwise deletion, you'd have to change your estimator. And the intermediate class is all about sums of squares and R-squares and like all the things that you can do by hand. And I didn't want to get into any of that in terms of changing the estimator. So you may have seen repeated measures ANOVA, and it is the same thing, but we're doing it using likelihood estimation so that we can have incomplete cases. And we're doing it as two choices out of infinitely many, some of which you'll see the rest of the semester. How's that? Okay. Then I'm picking up on slide 18 in lecture 3. And we'll be doing example 3B if you want to grab that too. So analysis of variance is a term in which we are predicting a quantitative outcome from categorical predictors. The question is, what kind of model for the variance does it have? And there are 3 kinds of ANOVAs that I want to compare and contrast here. Between persons is what I call it in the book. You probably know it as between groups or between subjects, as opposed to within subjects, which is the latter two. And there are 2 kinds of within subjects repeated measures ANOVA. They go by the names univariate and multivariate based on how their variance model is structured. The things they have in common. Question? Yes. Sure. Yes, so univariate and multivariate are under the umbrella of within subjects ANOVA or within groups ANOVA, or repeated measures. Those are synonyms. Repeated measures and within groups mean the same thing. Yep. So it's like the demarcation is whether it's between only or it allows some kind of within person correlation. Okay, so the things they have in common, they do not allow missing occasions, and that is not because of the model, it is because of the estimator. When people use the term repeated measures ANOVA, they usually are implying estimation using ordinary least squares. That is the problem. ANOVA is perfectly fine if your data fit it, but it's not perfectly fine to throw out whole people when you could use at least part of the data. Use as many occasions as you have would be the best strategy. They don't allow time-varying predictors. This is more of a software thing than like a theoretical thing. There's just nowhere to stick them in the sums of squares sort of way of organizing things. They do allow time invariant predictors, and those are known as covariates. So ANCOVA, as it is called, when you control for some other, usually a measured covariate that's person level, time invariant, level 2. They also all have the same model for the means with respect to how time is treated. And there is a new vocabulary word for that, saturated. It means time is being treated as a categorical predictor, so I am estimating as many fixed effects as I have occasions. So if I had 4 occasions, my model for the means, as we are going to call it, the fixed effects part of the model that generate expected outcomes, would have an intercept, and then T1 is a dummy code for whether or not it's time 1, T2 is a dummy code for time 2, and T3 is a dummy code. So we have 4 fixed effects that work together to perfectly recreate the 4 means. Now, there's nothing wrong with that, except when it's not as neat and tidy as this. Like if you have somebody that comes in at time 1.7 and 1.9 and 2.4, like where does that go in the equation? You'd have to have a new fixed effect for every possible time value. That may not even be possible. So another way of saying that is that time must be balanced and discrete. Everybody has to be on the same schedule, the same possible time points in these models. All of them have that in common. The way they differ is in their model for the variance. What we say about how the variances change over time or not, how the covariances change over time or not, and what that implies in terms of how many commonalities there are for people across people. Okay, with me so far? So here's the first one, and it's wrong for longitudinal data. Just put that out there. There's no way on earth this is ever right. So between groups or between subjects ANOVA, that's the E-only model. That's linear standard regression. If you stack your data so that all of your occasions are in one column and fit a standard linear regression, there is no way on earth that's right. Because what you are saying, here is another vocabulary word, an R matrix. This is the name that we're using for the variance over time on the diagonal and covariance over time on the off diagonal. So this would be an example of 4 balanced occasions. What we're saying is that the variance is the same no matter what occasion it is, and there's no covariance or correlation whatsoever. The occasions from the same person are independent. And I had a question in office hours the other day, thank you, where I realized that I had screwed this up aloud in class. So the YouTube captured it. Woohoo! All of my mistakes are forever on the internet. What a lovely feeling. I had said persons are independent and occasions are independent. Now, persons are independent, that is true, but that is going to be true the entire semester. That is not the point I wanted to make. Honestly, that was just me forgetting that I was teaching longitudinal and not clustered for a minute, because that was the last class I taught this material. And a lot of the slides have their subscripts changed and otherwise are the same, so I got caught on that. People are independent. That is an assumption that we will make the entire time. Can you guess what would happen if they're not? Like if kids are nested within schools? Anyone? Yeah, I'll take gestures. Add a level? Add another kind of you, essentially? Yep, that's what we would do. That will not happen this semester. It might happen next semester, though. I think I did 3-level models at the end of advanced last time, right? Didn't we do that? That sound familiar? Yeah, it was 2 years ago. I don't know, it's gone. I may have stuck it into clustered, yeah. I try to go like by popular request for the ends, like what the last unit is going to be. But anyway, we can change that assumption. People don't have to be independent. But in these models, the highest level is assumed to be independent. So if I have time at level 1 nested in people at level 2, that means people are independent. So that wasn't the point. The point was the occasions are independent, and that's the problem. So this structure is called independent in Stata. It's called variance components in SAS mixed. It's called a diagonal matrix more generally. Math people, can I get a judge's ruling? Yes? Any other words I should add to this list of what this pattern might be called? Nope? Good? All right, well, that's enough synonyms then. So that's the between one. That's sort of the straw man. We know that's not going to work. Now we get to the univariate repeated measures, the within subjects version. This is what we saw last time. This is U plus E. So we add this random intercept U0 term that gives each person their own mean. Remember that U0 is a deviation. It is how far off your mean is from the sample mean. So it has a mean of 0 because the mean is over being the fixed intercept. So fixed plus random intercept together gets you back to what your mean should be. From there, E is how far off your mean you are at that occasion. E is time specific. So we partitioned the total variability across persons and time into 2 sources. One is because some people are different from each other in their means. That's random intercept variance, this term here, tau squared sub U0. That's explained by people things. Why is it that some people are higher than others on average? Has to be a person characteristic that would explain that. E then is why are you higher right now than your mean? Well, it has to be a right now thing that explains that, time varying, level 1. That model implies a variance-covariance matrix over time, R matrix, that looks like this with this pattern. So the variability at each occasion is partly due to between-person mean differences at level 2, partly due to within-person residual differences at level 1, but it's the same amount of both that operates across time. And U0, its variance is all of what makes the off-diagonal covariances. And I know that looks weird, but think of it this way. What the model is saying is that the only reason why the occasions were correlated is because some people have a higher mean than others, and that's it. That's the reason. So the E's should be unrelated according to this model. This pattern has a special name called compound symmetry. That is what you would ask for in SAS and in one of the R packages I found. Exchangeable is what it's called in Stata, and that's because it doesn't care which occasion is which, right? Occasion 1 and 2 is just as related as occasion 1 and 4. So occasions are exchangeable in the same way that people could be exchangeable if they're nested in groups. So in the clustered class, this is the end of the story, right? We have our random intercept and then we start adding predictors. There's no other choices because occasions are specific entities that we have to pay attention to which is which, whereas people are treated as exchangeable. So here's why this isn't going to work for a lot of longitudinal data sets. The only way that the variances can stay the same over time is if people change at the same rate. Parallel lines, parallel growth. If people change differently, as shown in the bottom right picture instead, what happens to the variance over time? This can be a gesture question. What happens to the variance over time if people change differently? Does it stay the same? No. Yeah, it has to change. Yep. And actually, if you have a linear model of change where people need their own linear slopes, it changes in a U-shaped pattern where it's going to be a minimum at some point and that it increases on either side of that. So there is a pattern that is implied by that picture, very specific pattern. Yep. So to the extent that people don't change the same, this isn't going to fit. So what's the problem then? It predicts all the variances and covariances are equal. And if you think about how that would apply to hypothesis tests, remember we got different answers in terms of our p-values and standard errors when we had the U in the model versus not as a demonstration. Well, the same thing would happen. Let's say that you are interested in the difference between time 1 and time 2 and time 3, time 3 and time 4. Well, if time 4 has more variance around it, then using the same variance across all the times is going to mess it up. And if time 1 has less variance, then like that comparison will be messed up. So if the variance is not really the same, you can't pool it and use it for all the tests. The test should be like specific in terms of which variance goes with which occasion is relevant in that test. So that's the problem. Yeah?
Would that mean that regardless of what model we use, our fixed effects would be the same, but the level of confidence that we have in those predictions is what changes?
Exactly right. I'm going to repeat that for the recording. So that means that regardless of whether we have U and E and whatnot, the fixed effects will be the same. It's the level of confidence we have in them. So how the standard errors will differ based on the contribution of the variance. Yes?
Is this like the problem with like autocorrelation and taking like repeated measures? From the individual?
Say more about that. He's asking about autocorrelation.
So, like, too much dependency and you underestimate the standard errors?
Yes, I will say yes. This is in that lane. Like this is saying we have a constant correlation over time, whereas autocorrelation is a different pattern.
Okay.
That one says, and you're going to actually, this is Thursday. we're going to head there on Thursday, but just to foreshadow, that pattern says occasions that are 1 unit in time apart are correlated R, 2 units in time apart are R squared, 3 units are R cubed, R fourthed, R fifth, R sixth. There's not words for that, I don't think, after cubed, but that causes a decay in correlation over time, whereas this is constant.
Okay. And this is why we need multiple levels to account for the random effects, right?
we need to make sure that the pattern of correlation within a person is adequately captured by the model, and different kinds of models of change lend themselves to different patterns.
Yeah.
So you'd end up with probably a different choice if you had fluctuation kind of data where people aren't changing systematically, they're just kind of bouncing around a line, versus this kind of diverging, changing systematically. That will change the pattern that is likely to fit best.
Okay.
Good questions. Other questions? So this rarely fits longitudinal data. I've seen it fit 2 or 3 occasions, but after that, probably not. But to get the correct tests of the fixed effects, your data must only meet a less restrictive assumption called sphericity. At least one person nodded when I said this word. I think it was you, maybe. Right? Sphericity means that you are assuming that the differences between occasions have equal variance and covariance. That's what that means. It's a less restrictive condition. So if you only have 2 occasions, there's only 1 difference. So there's no way that you could have unequal variances across differences when there's only 1. Can't be wrong. So then what I learned to solve this problem, what did you learn? Do you remember? You just remember the word? Yeah. So I was like, so what you do is you find your SPSS output, and there's a test of sphericity, and if that test is significant, you go to look at the next box down instead. Does this sound familiar? And that box is filled with old people who named things after themselves. Like wind felt this, actually that's an Iowa people who named this, or someone else named it for them, not sure which. Greenhouse geyser is another one. Anyone else remember the names? There's a bunch of them, and these are all different ways to try and fix this problem. How far off from sphericity your data are, and they have this epsilon, this E-looking thing, that's supposed to capture that somehow, and it adjusts all of the model degrees of freedom and stuff. It's a Band-Aid, it's not a solution. It's the best that they had in like 1940 when they tried to solve this problem. It is, and I'm not going to hate on them for that. Like, they did not have the computing possibilities nor the theoretical developments that would be needed to move on. Mixed models came about in the 80s, if I'm not mistaken. And mixed models for longitudinal data in particular was a late 80s paper. It's fairly recent in the history of statistics. So we're not going to do any of that. Just put that box and the SPSS output aside. Here's your other alternative. And I never learned this in undergrad. Repeated measures ANOVA was this kind only. I didn't know there was another kind. But then I started teaching this stuff, and I'm like, hey, there's another kind. So multivariate approach to repeated measures ANOVA, or MANOVA. That may sound familiar. This one is like, you know what? I'm not going to try to predict what the pattern is. You do what you want. Let the data be what it wants. Unstructured is the name of this pattern, meaning just estimate each variance separately, estimate each covariance separately, and call it good. It'll work. So it is not really a model, it is just a recreation of the data. It will not be wrong. By the standard of what makes the data the tallest log likelihood, this will always fit best. Has to. It can be useful for that reason if you have complete data and balanced data. But here's the problem. Where is going to be occasion 1.4 and 2.8 and 3.7, right? You'd need as many separate rows and parameters and columns as you have occasions. So that starts to break down real quick when you have a lot of occasions, or unbalanced time, which creates a lot of occasions. So how many parameters does this require? Here's the formula. Does this formula look familiar to anyone who has been through SEM? And you better nod. This is how we used to compute degrees of freedom in SEM. That's not a coincidence. It's the same thing. In SEM class, we called this the H1 saturated model. It's the same exact concept. It's called unstructured today. Saturated in this unit is used to describe the fact that the model for the means is saturated with fixed effects for occasions, and unstructured is the variance model. But both terms conceptually mean the same thing. As many parameters as possible has to fit best. I will show you a modified version of this, by the way, that also includes random intercept variance. Stay tuned for that. Probably not Thursday, probably next week. And point is, this is the answer key, and I refer to it that way in the textbook. This is the right answer for the pattern. So what we would do, ideally, is try to find patterns that make this not worse, because it saves parameters and it improves your power. If you have extra parameters that you don't need, then that cuts down on the precision with which you can estimate stuff. Here is a question. In this model, univariate instead of multivariate, how many parameters are there in the model for the variance? How many symbols do you see on this slide? 2. Now, if I had 10 occasions instead of 4, how many symbols would we need? 2. If I had 100 occasions, how many do we need? 2. Yeah, so this scales. So 2, period, talking like the Gen Zers, they put a T at the end now. Period. They do. Versus this one, right? If I have 10 occasions, how many parameters do I need? Yeah, 10 times 11 is 110 divided by 2 is 55. And that's just this part. That has nothing to do with the predictors yet, right? That means at a minimum, you'd need 55 people to make this thing work, but that is a terrible idea. So this does not scale well. And it is for balanced data only. But when we have balanced data, this provides the answer key for what we're shooting for. So summarizing then, ANOVA approaches to longitudinal data are like t-shirts that say one size fits most. No, they don't. That's optimistic. There's really only 2 choices that introduce some kind of correlation of occasions from the same person. So standard between groups ANOVA says there is no correlation. Univariate version of within subjects repeated measures says there is a correlation, but it's the same over time. And multivariate says, yeah, whatever. Like there's no easy way to summarize that into a scalar equation. It's just the matrix itself. That's what it says the pattern is. In all of these things, time is treated as a categorical predictor. That means we have to have balanced data. We include as many fixed effects as we need to fully saturate all the means. Each occasion gets its own mean. And where we are headed is to get more flexibility with respect to both of these things. So we will end up adding fixed slopes related to time that allow us to predict the pattern of means, not just the mean for this, the mean for this, the mean for this. We're going to draw a line through them and try to figure out what the shape of that line should be. That allows people to have their own occasions and not have to have balanced time, because the line will go through whatever dots you got. That's the idea. On the other side of the model, we are going to introduce random effects, intercepts, and slopes. So each fixed slope related to time will have eventually a random part where each person gets their own version of it. Fixed means everybody gets the same, random means everybody gets their own. And what that does behind the scenes, like conceptually we like it because of the idea of individual differences in change, like there's a variance for that as a concept, but behind the scenes what it's going to do is create a pattern. Models of change that include more than a random intercept imply some kind of changing variance and covariance over time to go with it. So that's another pattern that we have at our disposal. All right. How are we doing so far? Questions? Go for it.
So if we go back to the previous slide, I'm trying to figure out what's the relationship of this random intercept to the ANOVA models versus the multi-level models. Do we have random intercepts in ANOVA models, but we can't have random slopes?
Yes.
But multi-level models can have both?
Yes.
Okay.
Yes. So a random intercept model, like the middle one, the univariate repeated measures, that is a multi-level model. It is. It's just a very limited case of one because there's only one kind of random effect. And the reason for that is because least squares. I think technically speaking, you could somehow hack a random slope model with least squares, but I've never seen it done. Does that help? Okay. And question for you?
Yeah. The answer for this may be very simple, but I'm like thinking in time points in terms of like sessions.
Okay,
It's like 1, 2, 3, and like for that, you can't have part of a session. Like it's
like if they
one-
leave early, it still counts as a session.
Right.
Okay.
So like when you're saying, time point of like 1.4, 2.8, 3.2, where's that coming from?
Okay, let me give you an example. I think I've used this example before, so forgive me if it's a repeat. Most of my jokes are repeats too, I apologize, but Let's say that you are measuring children in the fall, the winter, and the spring. But you can't measure them all on the same day. So you do them in groups of like 5 or something. You go into the school and you do that. Well, if you keep track of the distance between occasions, if some kids are measured like a month apart, some kids are measured a month and 4 days apart, some kids are measured a month and 6 days apart, right? Like that is what I'm talking about. It's the distance in between occasions
Okay.
that could vary across people because they're not being assessed at literally the same time.
Okay. That makes sense.
Okay. That also happens if you have people who differ in their age at the beginning. So then like time 1 is not the same age for everybody, and even if you had exactly measure them on the same day, they'll all be different ages at the next time too. So that's what I mean by time 1 versus 1.4 versus 2.5. Like it's just a continuous time metric rather than thinking about it as discrete, which is a session sort of way of thinking about it.
Okay.
Okay. Other questions? Thanks for talking today, guys. That's exciting.
So can these models allow for, I don't know, one kid comes in for 2 sessions and then they drop out of the study and then another person comes for 4 sessions or things like that?
Mhm.
How does that work? Like if the slope is not linear, do you not count the one kid that only has 2 data points because you can't map the trajectory compared to other people that have a nonlinear trajectory? Like does that limit the model? That was like a lot in one question.
It was, and I'm repeating it to make sure it gets on the recording because I don't know. Zoomers, can you hear the questions? Is the microphone working well enough? Yeah, that's what I thought. So I have a podcaster mic that's supposed to pick up the room, and it doesn't do as good of a job as I would like. So the question was, I'm going to take it in parts, and I'll probably forget some of it, so you'll have to remind me what I'm forgetting. But the first one is like, what if you have a kid who shows up once and never comes back? You do not have to dump that kid. You can use the one occasion they have, and that one occasion will contribute to the mean at that occasion. That kid will not contribute to anything in the model regarding change because they have no data to contribute. So could you use that kind of data that's incomplete? So incomplete and unbalanced are different things. Completeness is whether or not you showed up to the prescribed measurement occasions. Unbalanced is whether they're the same across people. So if you had everybody come in 4 times, that's complete. But if everybody didn't come in on the same 4 times, that's unbalanced. If everybody came in at the same time, but some people didn't come back, that's balanced and incomplete. So those are 2 different things. And whether we can use these models on incomplete data, I think is your question. The models, yes, but it's the estimation that makes the difference. If you tried to run standard repeated measures ANOVA that's built on sums of squares, you have to have everybody in every cell for that sum to work out. If you use likelihood estimation, you don't. You use the data that you have. Okay, that was one part of the question. And then there was more to it, though.
I think that was the gist. I was just thinking that we talked about before how you need, like, if you have nonlinear data, you need 3 data points instead of 2 data points.
That's what it
So I
was.
was just wondering that if the model, if it overall is fitting nonlinearly, that it would drop people that don't have the 2 occasions.
Gotcha. So if we had somebody who has only 2 occasions, other folks have 3 or 4, there's some kind of nonlinear change. The person with 2 can only contribute to the linear part because that's all they have. They would not contribute to the rest of it. You could still keep them in, though. So not everybody has to have 3 for it to work, to have random slopes. But the fewer people that do, the less likely you are to find them. It becomes a power issue at that point. But you can always try. Keep the data that you have is my recommendation, unless you don't trust them. Like if it's something to where, like if you have a survey with 100 items and somebody answers 1, Are you going to take that as like, oh, well, that's their survey score? Like, you got to really believe in that one item. You may adopt similar rules for different reasons about occasions. Like if they only come once, are they really part of the process that you're trying to measure? You know. One thing that you can do is put in the model as a covariate how many occasions someone has. Because it may be the case that the people who are going to drop out looked different ahead of time. Like there's foreshadowing that can be found. And if you wanted to be like, well, the people who came this time, here's what their parameters would be, and the people who came 2 times, this is what theirs would be, and we're going to kind of average it all back together, that's called a pattern missing model. Don Hedeker invented that too. Man's a genius, my personal hero. Hi, Don. Just in case, you never know. Maybe it will show up on his YouTube next video. YouTube does suggest things you're not subscribed to, so it could theoretically happen.
I've never been suggested a Don Hedeker video.
No, that's too bad. I don't know that he has a whole lot of them, but I'm just saying like maybe mine gets suggested because I have his name in it, you know, because they're listening to us. My brother tells me that that's not actually true, that the devices aren't actually listening, but damn if I don't talk about like buying something and then ads for it show up on Facebook in 30 seconds. It's creepy. So,
That's predictive analytics, and that's creepy.
it is creepy. It's also helpful. It's like, well, now I don't have to search for this. Thank you. Okay, did I get through the question?
Yes.
Excellent. No, don't apologize. Questions are great. Do you want to talk about estimation and model comparison a little bit? Said no one ever, but I got to do it. I got to. So, because we have these alternatives, right? We have like, let everything be what it wants, make everything the same over time, or make the off-diagonal empty, right? These are alternative choices. How do we decide between them? Well, we let the data decide. How we do that is model comparisons. So in doing models for the variance, which is what we're talking about, you may get a p-value that shows up on your output that's from a Wald test for it. Do not use those. Don't. Like R doesn't even show them. In SAS, they're not a default. Stata, I don't think, has p-values, but they have confidence intervals. We don't use Wald test. We don't do estimate divided by standard error is a t-value, it gets a p-value thing for these. What we do instead is model comparison. And I'm going to talk more about this in Unit 5. Chapter 5 of the book nearly killed me to write, to try and learn this well enough to be able to describe it. Jonathan helped a lot, as you might imagine. He keeps his patents behind him now on Zoom. Some of you saw him this morning. That's a household joke. He has patents for doing estimation, that's why. So he's good at it. So he's like the person I go to for help. But briefly, what I can tell you is that the index of how well your model works is essentially height as defined by some kind of distribution for your joint data. So it's multivariate height for all the occasions that you have, and the parameters of the model generate a height. And the question is, does the height get taller under this model versus that model? That's the big picture. What you get in terms of height, though, is going to vary. And what it means and what you can do with model comparisons is going to vary between 2 different definitions of height. So there are what I'm going to call flavors of maximum likelihood. Variants of it is what you might say instead. There is regular flavor maximum likelihood, which I abbreviate as ML. And in this context, I will never say ML again. You will hear me say ML. It changes because the alternative is something called restricted maximum likelihood or residual maximum likelihood, and that is pronounced REML. So we have ML and REML in this context. What you get from either of these things varies by software in somewhat of an annoying way. Because eventually we are going to need to multiply the difference in log likelihoods by -2 to create a hypothesis test, some software does you a solid and presents it to you that way. So in SAS and SPSS and some R packages, what you get in your output by default is -2 times log likelihood. In others, you get just straight log likelihood. And the relation between these is that log likelihood is height, given a distribution in log scale, And minus 2 log likelihood is shortness. It's backwards. Yeah. Zoom only on Thursday, Nikki. Or
Yep.
10, sorry. Yep. I forgot to announce that at the beginning of class, that we're getting kicked out of our classroom on Thursday. I'm displeased with this because I asked several weeks ago if this was going to happen, and I was told no, and then I was told yesterday, actually. So we will be meeting on Zoom only. It will be fun for me because that's the day that our house cleaners are going to come. So I'm going to be in my basement with the vacuum going above my head, trying to focus on class. It's going to be a good time. But if I try to do it upstairs, I'm worried that everyone in my hallway will hate me because the entire hallway will hear me lecture through our thin walls. So 6 of one, half dozen of the other. Zoom only on Thursday. Anywho, so shortness, then, we want smaller is better. Nobody wants to be short. Trust me on this. In log, like, what? You just, slow response, yes. I am vertically challenged, as some folks might say. Ostensibly, I am average height at 5'4", but I feel very short most of the time. So I think the world has gotten taller. So shortness, smaller is better. Minus 2 log likelihood. If it gives it to you in log likelihood, then bigger is better. So you got to pay attention to which you get. In all of my examples, by the way, I am going to ask for minus 2 log likelihood on your homework because that is essentially a fingerprint for your analysis. If you have the right variables in your problem, your minus 2 log likelihood will be correct. So will your log likelihood. So I, in each of my examples, have a way in code to ask for it if it's not already printed by default. It's stored somewhere in all the packages, so it's just a question of getting it out. So then the questions that would guide our model comparisons for choosing a model for the variance at this stage are pretty straightforward. How does the residual variance differ across occasions? Residual meaning leftover in this context, ANOVA language. And how are the residuals from the same sampling unit correlated? So is it a constant correlation across time? Is it an autoregressive correlation across time? Is there some other pattern that we might consider? Those are the questions that we want to ask. And comparing these models, nested models most of the time, where one model is a subset of the other, are done using what's known as a likelihood ratio test. It's also known as a deviance test in other contexts. And this term always confused me because likelihood ratio implies a numerator and a denominator. Well, it turns out that that's right if you're thinking of this in terms of likelihoods. But if you take the log likelihood, then what used to be division becomes subtraction. So then that's why we're subtracting one from the other because we're in logs, not regulars. Non-logs? I don't know. Judge's ruling? So if we're in the log scale, we subtract the values. But if we're in the non-log scale, is there a name for that? Unlog? Normal? Regular? I don't know. So what I have seen people do incorrectly in writing is say log likelihood ratio test. That does not work. If it's log likelihood, you are subtracting. If it's likelihood, you're dividing. And the same thing happens in computing the overall log likelihood too. If you have likelihoods for each person, they get multiplied together. That becomes a super tiny number real quick, and that's bad. But if you take the log of it, then instead of multiplying, you can add, and that's good. So we add together the log likelihood for each person's data, given the model parameters, sum that across people because people are independent, and then we get one number that summarizes how good the model is for fit. This is called the chi-square test in SEM because the chi-square test that shows up for model fit and structural equation models is a likelihood ratio test of your model versus the perfect model. Same thing. So here's how you compute these. It's pretty straightforward. Note in my notation, I'm avoiding H1 and HO because that's confusing. So I have fewer and more as my subscripts. Fewer means the model that has fewer parameters. More means the model that has more. Fewer always comes first. So if you are given minus 2 log likelihood, then you would compute the difference in minus 2 log likelihood, and it's written with this capital delta thingy here, the triangle thing. It is minus 2 log likelihood for the smaller model, minus that of the more model. So then the result must be positive. Because remember, being short is bad. So we want these to be as small as possible. So the model with fewer parameters will have a higher value than the model with more, yielding a positive result. If you are given log likelihood, the inside is still in the same order, fewer minus more, but then the result gets multiplied by -2 to flip it back around. Either way, your answer to this needs to be a positive number. If it's negative, you've done something wrong. The opposite is true in computing the degrees of freedom for this hypothesis test, which is how different your models are in terms of number of parameters. That's more minus fewer, because again, we need a positive number. The result you then compare to a chi-square distribution, where the degrees of freedom are the difference in model parameters, and the chi-square value is the difference in -2 log likelihood. So you can do this in software quite readily. There is a function in Excel that most of my examples, I have an Excel spreadsheet that goes with that shows computations, because I think it's helpful to see that written out sometimes. There's a function called chi-dist, it's a very old one. Stata has a built-in routine called LR test, and R has several things. ANOVA is the one that's more common. We're also going to meet one called RANOVA, one of my favorite jokes, because when I work with R, I feel like I've been run over. There's others too. Vladimir, are there others that you've come across that do likelihood ratio tests? No, those are the ones? Yeah, and if you can't find them, you can do it yourself. So you can find where -2 log likelihood is saved in the bowels of the object and literally do the math yourself. I had to do that in example 4 because the R package I picked didn't have a likelihood ratio test thing that worked with ANOVA. Of course not. So what this test is interpreted as then depends on your intent of this comparison. If you are starting it from the perspective of, I have a model, if I add stuff to it, does it help? Then if your test is significant, you would say, yes, the model fit has gotten better. If your test result is non-significant, you'd say it did get not better. Not worse, just not better. If you add things, it should help or stay the same. If you're approaching it from the opposite perspective, like you have something complex and you want to see if you can simplify, then a significant result means worse. The simpler one is too simple. If a non-significant result happens, then you would say not worse. I can simplify and not hurt fit significantly. This one I'd say is less common for folks, but again, drawing the parallel to SEM, this is what we do in SEM to judge model fit. Perfect answer key versus what I got. That's what we're going to do in this class. Unstructured as the answer key. Let all the variances and covariances be whatever the hell they want. Now I'm going to put a pattern to it. And does that make the model worse or not? So any test you can talk about either way. It's just a question of orientation. Are you trying to improve it or are you trying to simplify? Now that is not true for other pieces of information that come with this called information criteria. There's a whole bunch of these too. Some of them are named after people. But AIC Akaike, someone once told me. Can I get a judge's ruling on that from anyone? I tried. Bayesian information criterion is another one. There's AICC and like BICC. There's all different permutations. There's a whole bunch of people who did dissertations on this topic and like made their own version of it. But these are the two that are most common. Now note, what they start with is -2 log likelihood. So these are in smaller is better form, regardless of whether you get -2 log likelihood in your output or log likelihood. So sometimes your output is internally inconsistent in terms of what up means. Job security, woohoo. Question from the Zoomers. What is an example of when you would want to see if you can make your model simpler? So this is what we're going to do. I'll give you a couple slides back. So unstructured, multivariate repeated measures ANOVA. How many parameters are in this box in blue? 10. Okay, so do I need all 10? Yeah. What if I want to try and be cheap and come back to this box? How many are in here we had said? 2. So is 2 enough or do I need all 10? That's an example of when we would reduce. Does that help? Maybe?
So don't we know this by design?
Don't we know this by design? What do you mean by that?
I mean, by the data collection design. So we know that we are expecting people to vary across time, or we are expecting people.
I think that you can anticipate which models might be relevant to consider based on design and intent, but you never know what happens, right? You could design a study to measure individual differences in change and then not have any. Like that has happened. I've seen this happen to people, particularly if they don't have a lot of occasions or a lot of people. Because not having a lot of occasions doesn't give people room to show individual differences in change, and not having a lot of people doesn't give you power to detect it as a person-level variance. So you could start out that way, but be wrong. It could happen. And in that case, it would be overkill. If everybody changes the same, the 2 version is probably fine or close to it. Okay, back to this. Now, I had this slide all set up for years and years and years and years, and then I had to fix it because I started digging into R more and realized that it's inconsistent. So your first homework historically has been an activity designed to work with some of these rules as a vocabulary drill, actually, to compute AIC and BIC based on a description of the model. I realize I'm going to have to be very, very specific in the instructions for this time. But these things have number of parameters as one of their ingredients, and number of parameters is multiplied by 2 to create AIC. It is multiplied by the log, natural log, of some kind of index of sample size. And the rest of this depends on your software. So if you are in SAS, BIC, the size is number of people. Number of parameters depends on whether you are in EML or REML as an estimator. If you're in EML, number of parameters is both sides of the model, fixed and random. If you are in REML, it's the random variance side only. In R and Stata, they disregard that distinction. They count all the parameters, no matter whether you're in EML or REML. But then size differs by program. So I've seen it be total sample size in R and in Stata. I've seen it be persons in SAS, and I think in SPSS maybe. It depends on how the model's phrased. So these things will not agree across software packages until you adjust for all of these reasons why they might be different. But within a package, it's okay. Because the absolute values of these things don't mean anything. Like you'll get a number back that's like, oh, my AIC for this model is 2730. It's like, what's that? I don't know. It only has meaning relative to some other model. If I know that the AIC for some other model is 2750, then I'd say 2730 wins because it's smaller. And even though those numbers in R, for instance, might become, 2770 and then 2790, like the same rules will apply, smaller wins. So just be careful going across packages until you're sure that they're computing these things in the same way. If you stay within a package, you should be okay. Internally consistent is what we're going for. So these are converging evidence. Ideally, you would have all of these things agree. Like, for instance, if you're trying to simplify, then you would have a non-significant hypothesis test, and you would have AIC and BIC be a little bit smaller, but not really. In practice, no. You can have BIC be happy with you and AIC not. Likelihood ratio test says don't need that. BIC says yes, you do. Like they don't agree. I've seen in recent years, like people try to make rules for these things as to what smaller is. I don't know that those have taken hold. So I don't want to give recommendations based on that, but you may see that like, oh, this is a change in BIC of more than something, and then they cite some paper that says why. I'm not ruling it out. I'm just saying it's not a convention yet, to me. I could be wrong. 133, how are we doing? Are we hanging in there? Ish? Ish, all right. So the flavors. Let me give you the simplest version of it, and then you'll get the more complex version later. Do you remember back in intro stat, like an undergrad intro stat, and they're talking about the population formula for the variance versus the sample formula, and one is n and one is n minus 1? That's this. REML is n minus 1 and EML is n.
Can you say that again?
Yep, it's in the boxes here. So the two different types of maximum likelihood. There's the regular kind and there's the residual or restricted kind. The residual restricted kind, the first one here, this is the same thing as ordinary least squares if you have just a standard regression model. Like you could fit that in multi-level modeling software and get the exact same thing out of as you would a GLM package. It is the same thing. The difference is that this is more amenable to other types of models. It's more flexible. Did I assign the Enders chapters in this class? I probably did. Every class gets the Enders chapters. So if you're interested in like how that is or where this stuff came from, the Enders Missing Data Book chapters 3, 4, and 5 are the best explanation of maximum likelihood that I've seen. He makes it crystal clear. And he has pictures, and he has equations, and he has words, which should make everybody happy with some combination of that. I do not have the new Missing Data Book. This is from the 2010 version. He did come out with a new one in last year. I'm looking forward to seeing that one. But that's where I would recommend, is those particular readings, which should be helpful. So the reason that I'm drawing this analog here is because in standard ordinary linear regression, ordinary least squares, all of the variances are computed taking into account the number of parameters. So you have this k thing here. That's the number of fixed effects. So you would have one at a minimum, and then however many other predictors contributing to this. Versus regular flavor maximum likelihood is like the population version of the formula for variance where it's only n. This is the version that is the only choice for most other kinds of models. So residual maximum likelihood is only a possibility for models that have some kind of conditionally normal residual. Standard types of models. If you have a generalized model, so predicting some kind of not normal outcome, or anything in the world of latent measurement models, that's regular flavor maximum likelihood. So like you never heard about REML in SEM class because it's not a thing. It is not built into any SEM software package, although theoretically it could be. The reason for that, though, is they assume you have enough people to where the differences between these things don't matter. So given the same numerator, which of these is going to result in a bigger value? 50-50 shot. The first one or the second one? The first one, yep. And that's why this matters. In smaller samples, the maximum likelihood version is going to be too small. REML is the right answer. This stops mattering after about, it depends on the complexity of the model, but 50 to 100 people stops mattering after that. But if you have very small samples, you'd want to pay attention to this. REML is the default in every MLM package that I'm aware of. And that's what we're going to stay in this semester because a lot of us don't have large samples. Both of these things are what are known as full information estimators, meaning they use all of the original data to judge the height of the data and find the model parameters that make the height the tallest. That is in contrast to limited information, which uses a summary of the data in estimating the model parameters, usually some kind of correlation matrix. So you will also see, adding to our acronym soup, I told you this was ML or EML. You will also see this called FIML, F-I-M-L. That is the same thing because limited information is not really a thing in these models, not with conditionally normal residuals. That's not a thing. So the default is full information. And for whatever reason, REML doesn't have an FI in front of it. So for years, I've been trying to make FREML a thing, but just like fetch, it's never going to happen. But don't get it twisted. There's nothing like special about FIML with respect to missing data that isn't also true of REML. FIML is what people say when someone is arguing with them about whether they're missing data or missing at random. It's like, well, I used full information maximum likelihood for my missing data. Well, guess what? I used full information residual maximum likelihood. Take that. Yeah, mic drop. So we're going to stay in REML, but I want you to know this distinction because it changes the rules for how you do model comparisons. And I have many slides on this presented in different ways because I couldn't settle on which one I like best, so I gave you all of my ideas. But rules for the likelihood ratio test. In REML, we want to use this because the variances we get back are unbiased. They should be accurate, especially in small samples. But we cannot compare models that differ in their fixed effects. The definition of height is different in that case. Another way of saying this is that REML operates on the residuals of the model and not the data. There is a paper that is like 2 pages long and filled with equations from 1974. I want to say Harville figured this out. Impenetrable. But those were the few words that I understood. Maximizes the likelihood of the residuals, not the data. Okay, that I can take with me. Thank you, sir. I believe he's from Iowa as well, in the stat department. Maximum likelihood maximizes the height of the data, the whole thing. So that means that you can compare models that differ in fixed effects, random effects, both, whatever you like. Here's a side-by-side. So in software, you will see some abbreviation of ML or REML. Usually it's tied to a method option in software. And your output will say something like this to differentiate which you have. In estimating the variances, it treats the fixed effects as either known in ML. It doesn't adjust the degrees of freedom. That would need to be factored in order to know what the variance is left over. REML treats them as unknown. So the corresponding variances will be too small in ML, but unbiased in REML. But because it indexes the fit of the entire model in ML, that means you can compare models that differ in any way, whereas REML indexes really the fit of the variance model specifically, and so the models to be compared must have the same fixed effects. One more. Here's a table. What type of comparison? Nested. So one model is a subset of the other. This is what you can do. If you're interested in what the fixed effects hypothesis test would be, you can stare at the p-values straight on the output, estimate divided by standard error, create some kind of t, possibly a z if there's no degrees of freedom involved for the denominator, and then that's fine. So you can always do that. But you cannot do -2 log likelihood comparisons if you're using REML. If you're interested in comparing random effects or the model for the variance more broadly, you should not use the default wald test p-values. You should do some kind of likelihood ratio test, preferably in REML. And if you want to do both, that's an ML thing, not REML. For non-nested, that is rarer, but does happen. So different kinds of correlation is an example. So an AR1 model is what it's going to be called that Alex mentioned earlier. Shout out. That has 2 parameters also. So if you want to say, do I have a constant correlation or an AR1 correlation, it's each 2 parameters. You can't do a likelihood ratio test to decide. So that's where you would go to AIC and BIC, but only keeping the same fixed effects if you're in REML. And one other giant thing across the top, and then I think we'll be done for the day. Do you see this? All observations must be the same. So where this shows up is when you add predictors, and not everybody has all the predictors. Because what happens to the cases that are missing anything that goes into the model is that they get dropped. The rows have to be complete. So if you create a sum across a different number of cases, that sum is no longer comparable to the original sum using all the cases. So this is the thing to be very watchful about. Your log likelihoods are on different scales if you change the sample size. All right. There. Words, no tables. So I am going to teach you a process that makes it the least challenging to get it right. We're going to use REML for everything. We're going to use Wald tests for fixed effects. We're going to use likelihood ratio tests for everything else. That follows the rules in the simplest possible way. Ta-da! We made it. And I get to do example 3B next time, it looks like. So 144, time for any questions?
Can you say again the 3 things that we're going to do in this class?
Yep. So I'm going to make this simpler, hopefully. We're going to use REML all the time, except when it's not available. So certain model things are not available, but mostly available. We are going to use Wald tests for the fixed effects. So the p-values that show up next to the slope on the output, those are fine. But to ask questions about the model for the variance and whether we need like 2 or 10, just a random intercept or more stuff, that's likelihood ratio tests, differences in -2 log likelihood to answer that question. And we'll phrase it as nested model comparisons whenever possible. Okay, all right, 144. It was garbage day, that means I say see you Thursday, but from my basement. All right, thanks folks, see you then. Let me know if you need anything.